Let's look at some more examples. The limit of ln of 1 minus x over x as x tends to 0. This too is 0 over 0 because the numerator tends to ln of 1, which is 0, and denominator goes to 0. So this is a 0 over 0 type. Therefore, by LHopital's rule, is equal to the limit as x tends to 0 of derivative of the numerator divided by derivative of the denominator. And that is equal to the limit as x tends to 0 of derivative of natural log is 1 over 1 minus x, but by chain rule we multiplied by minus 1. Derivative of x is 1. So now when you let x go to 0, what do we get? Negative 1 in the numerator over 1, negative 1 over 1 over 1, which is just negative 1. And here something, whether x goes from the left or from the right, it's still positive 1 due to the fact that if x goes to 0 from the right, denominator is positive, and then because x is 1 minus x is less than 1, because x is positive, you're subtracting from 1. ln of a number less than 1 is negative, over positive will give you negative. And also when x is negative, denominator would tend to 0 from the left, so x is negative in that case. And then here when x is negative, you're subtracting a negative number from 1, you make it bigger than 1, and ln of that is positive, so positive over negative is negative. In either case, from right or left, it's still negative 1. So here's another example, the limit of ln of x over x as x tends to infinity. This is infinity over infinity type, because ln of x tends to infinity, because it's an increasing function without bound. So this is the graph of ln of x. It keeps going up, but slowly but surely. So it is infinity over infinity type. Therefore, LHopital's rule applies. So this is the same as the limit as x goes to 0 of derivative of the numerator over derivative of the denominator, which is the limit of, in the numerator, derivative of ln of x is 1 over x. The denominator, derivative of x is 1, and x tends to, it's supposed to be infinity because I've been writing 0 too many times. So that should be the limit as x tends to infinity, not 0. And then this would be the limit of 1 over x over 1 as x goes to infinity. The numerator goes to 0 because when x, its denominator gets bigger and bigger, when you divide by bigger and bigger numbers, the number gets smaller and smaller. So that's why it tends to 0. So the answer is 0 over 1, which is just 0. So ln of x over x as x tends to infinity tends to 0. So here's another example. We have 1 over x in the numerator, ln of x in the denominator. X tends to 0 from the right. The numerator would tend to infinity because you're dividing 1 by small numbers, and those small numbers tend to 0. And it's from the right, so it would tend to positive infinity. In the denominator, we know if this is the graph of ln of x, and as x tends to 0, ln will tend to negative infinity. So denominator tends to negative infinity. And this is considered infinity over infinity type. And again, L'Hopital's rule applies. So this is the same as the limit as x tends to 0 from the right of derivative of the numerator over derivative of the denominator. So this is the limit as x tends to 0 from the right of derivative of 1 over x is minus 1 over x squared. That's by power rule. Derivative of ln of x is 1 over x, and this can be simplified to the limit as x tends to 0 from the right of minus 1 over x, because you can multiply both numerator and denominator by x, so you have x over x squared, which is 1 over x with a minus in front, and that is equal to x goes to 0 from the right, so 1 over x tends to infinity with a minus in front. It would be minus infinity. Or you can also say the limit doesn't exist as a real number. Here's another example. This 2 as x goes to infinity is infinity over infinity, and by L'Hopital's rule, it's the limit as x tends to infinity of derivative of the numerator, derivative of ln of x divided by derivative of the denominator, which is equal to the limit as x tends to infinity of 1 over x over 1 over 2 square root of x. Derivative of square root of x is 1 over 2 square root of x. And then when you simplify this, you get the limit as x tends to infinity of, if you multiply both numerator and denominator by 2 times the square root of x, you get 2 times square root of x over x, and that ratio would be square root of x in the denominator. And as x tends to infinity, square root of x tends to infinity, 2 over infinity would tend to 0, right? Because the denominator is getting bigger and bigger. So here's one more example. The limit of 1 minus cosine x over x as x goes to 0. The numerator tends to 1 minus 1 because cosine of x tends to 0 as x tends to infinity. You can see it on the unit circle. This is the cosine axis, and here's where the 0 is from the right or the left. Cosine tends to 1, and then denominator goes to 0, so we have 0 over 0 type, which can be done by L'Hopital's rule, and that is the same as taking derivative of the numerator divided by derivative of the denominator, which is the limit as x tends to 0 of derivative of the numerator. Derivative of 1 is 0 minus derivative of cosine x is minus sine x. Denominator as derivative is 1. As x goes to 0, sine x goes to 0. You can see it from the unit circle. This is the sine axis. So sine is 0 here. The y coordinate of that point is 0. So 0 over 1 is a 0. In fact, this limit, we used it in derivation of the derivative for sine and cosine, but of course we did not use L'Hopital's rule to find the limit. We used geometry, in regular calculus books. They use geometry for the sine x over x and 1 minus cosine x over x as x tends to 0 to find their limits. There will be other types of indeterminate forms that we consider in the following videos.